in this lecture we'll answer two questions. In the first question we find out the area of this pentagon ABCDE, and the second question we find out the area of this ring shape. So we'll start with the first question. In the drawing we have pentagon ABCDE. So what is a pentagon? A pentagon is a flat closed shape with 5 straight sides and 5 interior angles. This is pentagon ABCDE. It has 5 sides, 1, 2, 3, 4, 5, and 5 interior angles. 1, 2, 3, 4, 5. So in the drawing we have pentagon ABCDE. Know that this is side ED is equal to side EA is equal to side BC. They are both all of the sides are equal to 1 unit in their lengths. Side DC equals to x units in its length, and side AB equals to 1 on x units in its length. Those two angles are both right angles. Again, our task is to find out the area of this big pentagon ABCDE. So first of all, we will join points E and B together by a straight line. And we join points E and C together by a straight line. In the next step, we will extend side BA in such a way that the extended part will be equal to x units in its length. We define this point as point M. But again, the extended part AM is equal to x unit in its length according to our construction. In the next step, we join points E and M together by a straight line. By joining points E and M, we created the right line EAM. Actually, before that, we know that BA is one side of the big pentagon ABCD. So BA is the side of a pentagon. It is absolutely a straight line. When you extend the straight line BA by a straight line, the result BM must be also a straight line, because when you extend the straight line by a straight line, the result must be a straight line. So BM is a straight line. If you focus on the upper side of the straight line BM at point A, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the areas from one side of the straight line is equal to 180 degrees. So which areas we have there at the upper side of the straight line BM at point A? We have this angle that is the right angle, plus this missing angle, and so that the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So by joining points E and M together by a straight line, we created the right triangle EMA. In the next step, we will prove that those two right triangles can move into each other according to side angle side rule. So we have to prove that this right triangle EMA, right triangle EMA, can point to this right triangle EDC according to side angle side rule. So why those two triangles can join to each other? First of all, those two sides, they are both equal to x and therefore they are equal to each other. This is side MA of the right triangle EAM, and it is equal to this side, side DC, of this right triangle EDC. And again, we should find out that side MA of the right triangle EMA is equal to side DC of the right triangle EDC. They are both equal to x and therefore they are equal to each other. In addition, those two angles, they are both equal to 90 degrees and therefore they are equal to each other. So here this is again EAM. In the right triangle EMA, and it is equal to this angle, this is actually angle EDC. In the right triangle EDC. This again, I should find out that angle EAM in the right triangle EMA is equal to angle EDC in the right triangle EDC. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides, they are both equal to 1 and therefore they are equal to each other. So here this is side EA on the right side, EAM. It is equal to this side, that is actually side ED on the right side, EDC. So okay, again, I should remember that side EA on the right side EMA is equal to side ED on the right side EDC. They are both equal to 1 and therefore they are equal to each other. So if you found out that those two sides and the angle that is included between those two sides in this right triangle EAM are correspondingly equal to those two sides and the angle that is included between those two sides in this right triangle EDC. And therefore, those two right triangles are congruent to each other according to side angle side rule. We have those two sides and the angle between them in this triangle EAM are correspondingly equal to those two sides in this right triangle EDC. And therefore, those two right triangles congruent to each other according to side angle side rule. If you found out that the right triangle EMA congruent, this is the sign of congruent, to the right triangle EDC according to side angle side rule. And from the fact that those two right triangles congruent to each other, we will derive two things. First of all, we derive that those two right triangles has the same areas. That is to say, the area of this right triangle EMA is equal to the area of this right triangle EDC. Because of the fact that any two triangles that can go into each other, they must have also the same areas. So, we derive that the area of this triangle EMA is equal to the area of this triangle EDC. And the first thing, again, the area of triangle EMA is equal to the area of triangle EDC. The second thing that we will derive that from the fact that those two right triangles can go into each other, we derive that side EC of this right triangle EDC is equal to side EM of this right triangle EDC. So now, I should find out that EC equals to EM. or side MA on the right triangle EMA is equal to side EC on the right triangle EDC. So actually we found out that because of the fact that those two right triangles can go into each other, they have also the same areas. That is to say, they have this green right triangle EDC is equal to the area of this green right triangle EMA. So actually, if we define the area of this green right triangle EDC as Z, that is to say it is equal to Z's coordinates in its size, then the area of this green right triangle EMA must be also equal to Z's coordinates in its size because they have the same areas. In the next step, we find out the length of this line segment MB or side MB. What is the length of line segment MB? MB equals to MA plus AB. MA plus AB. So as a normal, if you hold the length of line segment MB is equal to MA plus AB. So MB in total equals to MA, that is X, plus AB, that is 1 minus X. So in total, if you found out that MB is equal to X minus X is 0, so we left only with 1. MB equals to 1 unit in its length. This is side MB, that equals to 1 unit in its length. In the next step, we will prove that triangle MEB can go into this triangle PEC according to side rule. Again, we prove that those two triangles can go into each other according to side rule. So we have to prove that the right triangle, this is not the right triangle, triangle MEB, this is triangle MEB, its congruence to this triangle EBC according to side rule. So, why those two triangles can go into each other? First of all, we already found out that EC equals to EM, or EM equals to EC. EM equals to EC. So, as we know, side EM of this side EMB is equal to side EC of this side ECB. Here we already found out that side EM of triangle EMA is equal to side EC of triangle EC. Here, EC is side triangle MEB is equal to side EC of triangle EBC. In addition, those two sides, those two side MB of line EMB is equal to side BC of line EBC. They are both equal to 1 and therefore they are equal to each other. MB equals to BC. And again, side MB of line EMB is equal to side BC of line EBC. They are both equal to 1 and therefore they are equal to each other. And finally, side EB, the common side that belongs to both triangles. It is very easy to say that side EB belongs to triangle EMB and EB also belongs to triangle EBC. So if you know that EB equals to itself, it's a common side that belongs to both triangles. EB equals to itself, it's a common side that belongs to both triangles. So if you found out that all the three sides of this triangle EMB are corresponding equal to all the three sides of this triangle EBC, and therefore those two triangles can go into each other according to side, side, side rule. So if you don't, if you found out that triangle EMB congruent, this is the side of congruent to triangle EBC according to side, side, side rule. And from the fact that those two triangles can go into each other, we will derive that they have also the same areas. That is to say, we will derive that the area of this triangle EMB equal to the area of this triangle EBC. It again, if you found out that the area of triangle EMB is equal to the area of triangle EBC because they can go into each other. In the next step, we will find out the area of this triangle EMB. So what is the area of triangle EMB? Actually, we know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of this triangle EMB must be equal to the base MB times the height AE over 2. It again, the area of triangle EMB must be equal to the base MB times the height AE over 2. We already found out that MB equals to 1 times AE. AE also equals to 1 divided by 2. So in total we found out that the area of triangle EMB is equal to 1 times 1 over 2. 1 times 1 is 1, so total is equal to 1 over 2, that is 1 half. And again, in total we found out that the area of triangle EMB is equal to 1 half square units in its size. So you can write here that the area of triangle EMB is equal to 1 half square units in its size. And from this equation, 1 half equals to the area of triangle EMB equals to the area of triangle EBC. We derive that the area of triangle EBC also equals to 1 half square units in its size. Those two sides are equal to each other. So the area of triangle EBC is also equal to 1/2 square units in its size. In the next step, we will focus on this big quadrilateral EMBC. The area of this big quadrilateral EMBC must be equal to the sum of the areas of the shapes that it consists of. Quadrilateral EMBC consists of two shapes. It consists of this triangle EMB and it consists of this triangle EBC. And therefore, the area of the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the sum of the areas of those two triangles that it consists of. So, the area of quadrilateral EMBC must be equal to the area of triangle EMB plus the area of this triangle EBC. Repeat again. The area of the big quadrilateral EMBC must be equal to the sum of the areas of the shapes that it consists of. Quadrilateral EMBC consists of two shapes. It consists of triangle EMB and it also consists of triangle EBC. And therefore, the area of the big quadrilateral EMBC must be equal to the area of triangle EMB plus the area of triangle EBC. We already found out that the area of triangle EMB is equal to 1/2 plus the area of triangle EBC, that is also equals to 1/2. 1/2 plus 1/2 is 1. So in total, we should find out that the area of the big quadrilateral EMBC is equal to 1 square units in its size. From one side, but from the other side, if we look on the big quadrilateral EMBC in a different way, we can see that this big quadrilateral EMBC consists of two other shapes. It consists of this green white triangle EMA and it also consists of this quadrilateral ABCE. And therefore, the area of the big quadrilateral EMBC must be equal to the sum of the areas of those two shapes that it consists of. So in total, the area of the big quadrilateral EMBC must be equal to the area of this green triangle EMA plus the area of this quadrilateral ABCE. Again, if we look on the big quadrilateral EMBC in a different way, we find out that quadrilateral EMBC consists of two shapes. It consists of the green right triangle EMA, it also consists of quadrilateral ABCE. And therefore, the area of the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes of those two shapes that it consists of. It is the area of triangle EMA plus the area of quadrilateral ABCE. So, from this long equation, we learn that those two sides are equal to each other. Those two sides are equal to each other. That is to say, 1 equals to the area of the green right triangle EMA plus the area of quadrilateral ABCE. So to that, we have found out that the area of the green right triangle EMA plus the area of quadrilateral ABC equals to 1. But according to our definition, the area of this green right triangle EMA equals to Z squared in its size. So we can substitute the area of the green right triangle EMA by Z. In total, we get that 1 equals to Z plus the area of quadrilateral ABCE. In total, we have found out that 1 equals to Z plus the area of quadrilateral ABCE. Our task is to find out the area of the big pentagon ABCDE. So what is the area of the big pentagon ABCDE? Actually, the area of this big pentagon ABCD must be equal to the sum of the areas of the shapes that it consists of. The big pentagon ABCD, the big pentagon ABCD consists of only two shapes. It consists of this green right triangle EDC, and it consists of this quadrilateral ABC. And therefore, the area of the big pentagon ABCD must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to the area of the green right triangle EDC plus the area of this quadrilateral ABCE. Again, the area of the big pentagon ABCDE must be equal to the sum of the areas of the shapes that it consists of. The big pentagon ABCD consists of only two shapes. It consists of the green right triangle EDC. It also consists of the big quadrilateral ABC, and therefore the area of the big pentagon ABCD must be equal to the sum of the areas of those two shapes that it consists of. Consists of only those two shapes and not anything else. I already found out that the area of this triangle EDC equals to Z. So I can substitute the area of triangle EDC by Z. So it equals to Z plus the area of quadrilateral ABCE. So in total, we found out that the area of the big pentagon ABCDE is equal to Z plus the area of quadrilateral ABCE. But we already found out that Z plus the area of quadrilateral ABCE equals to 1 here. So we can write here that Z plus quadrilateral ABCE equals to 1 according to what we have already found out. And from this long equation, we will have that the area of the big pentagon ABCD is equal to 1 squared in size. This is the long equation. From this long equation, we will have that the area of the big pentagon ABCD equals to 1. So the area that we are looking for in this question, that is the area of the big pentagon A, B, C, D, E in total it is equal to 1 square unit size. 1 square unit size. So again I should find out that the area of this big pentagon ABCDE is equal to 1 square unit size. So finish with the first question. The next step I will present to the second question. I will solve the second question of this lecture. Our task in the second question is to find out the area of this green shape. The green shape it is actually triangle A and B. This is triangle A and B. So we have to find out the area of the green triangle A and B. This is the green shape. It is given us the question that chord AB is the diameter of this circle. So as you know, chord AB is the diameter of this circle. In addition, we know that those triangles are both right angles. PQ is a tangent to the circle at point M. Point M is the point of tendency of tangent PQ with this circle. In addition, we know that AP equals to 9 units in its length. PQ equals to 4 units in its length. Again, our test is to find out this green shape that is actually the green triangle A and B. So first of all, we implement rule 7 in our drawing. Repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is called AB, that is the diameter of the circle. This is peripheral angle ACB, that subtends on chord AB, that is the diameter of the circle, and therefore peripheral angle ACB must be equal to 90 degrees in its size according to this rule 7. So according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. We can definitely implement rule 7 in our drawing. Why? Because we have peripheral angle A and B. This is peripheral angle A and B that subtend on the diameter of the circle. This is called AB, and therefore peripheral angle A and B must be equal to 90 degrees in its size according to rule 7. In the next step, we define this angle, this angle PAM as alpha. So in the right side APM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. PQ is a tangent to this circle at point M. So PQ is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PQ at point M? We have this angle that is equal to 90 degrees minus alpha, this angle equals to 90 degrees, plus this third missing angle, that is angle BMQ. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. So, write it down. If you found out that 90 degrees minus alpha plus 90 degrees plus this missing angle, the circular angle BMQ. Total the sum of those three angles must be equal to 180 degrees according to rule 3. Again, 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ must be equal to 180 degrees according to rule 3. 90 degrees plus 90 degrees, it is 180 degrees, so we have 180 degrees plus the missing angle BMQ minus alpha equals to 180 degrees. So write it down. (180 degrees) plus the missing angle BMQ minus alpha is equal to 180 degrees. So here we have 180 degrees on both sides of this equation, so 180 degrees will get cancelled, and you left only with the missing angle BMQ minus alpha equals to 0. Here we add alpha to this equation and get that the missing angle BMQ is equal to alpha degrees in its size. This is the missing angle BMQ. This is the missing angle BMQ. This is equals to alpha degrees in its size. So in this small right triangle BMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. It is very easy to see from the drawing that those two right triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to alpha, and therefore they are equal to each other. So we found out that all the angles of this big right triangle APM are corresponding equal to all the angles of this right triangle BMQ, and therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. We found out that this big right triangle APM is similar this is the sign of similar to the right small triangle BMQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AP of this big right triangle APM, or side MQ of this right triangle PMQ, is equal to side PM of this big right triangle APM, or side BQ of this big right triangle BMQ. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle APM on side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM on side BQ of the small right triangle BMQ. AP equals to 9 over MQ. MQ is the missing side, so notice it is. And it is equal to PM. PM is also the missing side, so we leave it as it is. Over BQ. BQ equals to 4 units in its length, according to what is given as the question. So in total, we have found out that 9 over MQ equals to PM over 4. Here we will cross multiply this equation, and we get that MQ times PM is equal to 9 times 4, that is 36. So in total, we have found out that MQ times PM equals to 36. In the next step, we will define the center of this circle. This point is point O. So actually, always the radius of the circle that we will define as R, OB is also the radius of the circle that is equal to R according to our definition. In the next step, we will join points O and M together by straight line. M is the point of tendency of tangent PQ with this circle. Point O is the center of the circle, point M is the point on the circle itself, therefore OM is the radius of the circle, is equal to R. The radius OM that equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent PQ with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees in size according to rule 1. In the next step, we will do a construction. That is to say, from point O, that is the center of this circle, we will draw perpendicular on side AP. Again, from point O, we will go perpendicular on AP. So okay, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and AP. This point is point L. When doing this construction, we get the big quadrilateral LOMP. Inside the big quadrilateral LOMP, we have 1, 2, 3 rectangles. The sum of 3 rectangles is equal to 270 degrees. So 270 degrees plus the size of this 4 triangle, the total must be equal to 360 degrees according to the rule that the sum of the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 triangle must be equal to 90 degrees in its size. So inside the big quadrilateral LOMP, we have 4 rectangles, and according to rule 5, any quadrilateral that has 4 rectangles must be this rectangle plus a square. So we need to this big quadrilateral LOMP is a rectangle because it has 4 rectangles. In the next step, we will do another construction, that is to say from point B we will draw perpendicular on the radius OM. Again from point B we will draw perpendicular on the radius OM. So actually this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and the radius OM. This point is point S. So by doing this construction we get the small quadrilateral SBQM. Inside the small quadrilateral SBQM we have 1, 2, 3 rectangles. And therefore this fourth rectangle must be also equal to 90 degrees in its size. Therefore quadrilateral SBQM is a rectangle because it has 4 right angles. So it is known. The small quadrilateral SBQM is a rectangle according to all 5. In the next step, we'll focus on the big quadrilateral LO, on the big rectangle, it is a rectangle, on the big rectangle LOMP. We know that the opposite sides of a rectangle are parallel to each other. So in rectangle, the big rectangle LOMP, side LP is parallel to the opposite side OM. Again, in the big rectangle LOMP, side LP is parallel to the opposite side OM. But LP is part of the straight line AP. Again, LP is part of the straight line AP. And if a part of the straight line is parallel to another straight line, then the straight line AP itself must be also parallel to the other straight line OM. So if you want to know that AP is parallel to OM. AP is parallel to the radius OM. In the next step, we copy those two power lines AP and OM and the diameter AOB in a new page, and we will implement all 50 on the new drawing. Okay, those are the two power lines AP and OM. This is the diameter AOB of the circle. Those two angles are defined as corresponding angles and they are located between the power lines AP and OM and therefore they are equal to each other according to rule 50. On rule 50. According to rule 50, corresponding angles between power lines are equal to each other. In the drawing you have line A, that is parallel to line B. The red line C cuts the two power lines at those 2 points. Those two angles, alpha and beta, are defined as corresponding angles and they are located between the power lines A and B and therefore they are equal to each other in their sizes. This is to say alpha equals to beta. And definitely implement rule 50 in our drawing. we have those two corresponding angles that are located between the parallels AP and OM, and therefore they must be equal to each other in their sizes. So those two angles are equal to each other. So if we define this angle as beta, then this angle must be also equal to beta because they are equal to each other according to Rule 50. So if we found out in conclusion that angle PAO equals to beta, this is angle PAO that is equals to beta. Again, PAO equals to beta degrees in size. In addition, we also found out that this is angle MOB that is also equals to beta degrees in size. Angle MOB is equal to beta degrees in size. This is angle MOB that is equal to beta degrees in size according to Rule 50. So in this right green triangle OSB, this angle equals to beta, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus beta, according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the upper right triangle ALO, this big angle is equal to beta, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus beta, according to the same rule that states that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that those two right triangles can go into each other according to angle side angle rule. So why those two right triangles can go into each other? So I write it down. Actually, have to prove that the upper triangle, the upper right triangle ALO, this right triangle ALO, can go into this green right triangle SOB. So why those two right triangles can go into each other? First of all, those two angles they are both equal to beta and therefore they are equal to each other. So actually, this is angle LAO in the right triangle OLA, and it is equal to this angle, that is a triangle SOP, in the right triangle OSB. And again, I should found out that angle LAO in the right triangle ALO is equal to angle SOB in the right triangle SOB. They are both equal to beta and therefore they are equal to each other. In addition, side AO on the right triangle ALO is equal to side OB of this right green triangle OSB. They are both they have the circle that is equal to 1, therefore they are equal to each other. So I write it down. AO equals to OB. And again, I should remember that side AO of the right triangle ALO is equal to side OB of the right triangle SOB. They are both they have the circle that is equal to 1, and therefore they are equal to each other. And finally, those two sides are both equal to 90 degrees minus beta, and therefore they are equal to each other. So actually, this is again AOL. In the right triangle, ALO, and it is equal to this angle. This is actually angle OBS. In the right green triangle, OSB. Okay, again, I should know that angle AOL in the right triangle ALO is equal to angle OBS of the right triangle OSB. They are both equal to 90 degrees from each other, and therefore they are equal to each other. So I actually found out that those two angles and the side that is included between those two angles in this right triangle ALO correspondingly equal to those two angles and the side that is included between those two angles in this right triangle OSB, and therefore those two right triangles can go into each other according to angle side angle rule. So write it down. I found out that the right triangle ALO convert, this is the sign of convert, to the right triangle OSB or OBS according to angle side angle rule. That is to say, repeat again, that those two angles and the side that is included between those two angles in the right triangle ALO are corresponding equal to those two angles and the side that is included between those two angles in this right triangle OSB. And therefore those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we derive that LO equals to SB. LO equals to SB. Why LO is equal to SB? Actually, LO equals to SB according to the rule that corresponding sides that can go in triangles are equal to each other. That is to say, those two right triangles can go into each other, and therefore the two corresponding sides, that is to say, LO and SB, must be also equal to each other and their lengths. So if we define the length of side LO as x, then the length of side SB must be also equal to x because they are equal to each other. We know that the opposite sides of a rectangle are equal to each other. So in the big rectangle LOMP, side LO must be equal to the opposite side PM, but LO equals to x, therefore the opposite side PM must be also equal to x units in its length. Likewise, in the small rectangle SBQM, side SB must be equal to the opposite side MQ, but SB equals to x, and therefore the opposite side MQ must be also equal to x units in its length. We already found out that MQ times PM equals to 36. Write it down. Found out that MQ times PM equals to 36. MQ times PM equals to 36. MQ is x times PM. PM is also x. So total MQ times PM equals to x times x, this equals to 36. X times x equals to 36. X times x is x squared, is equal to 36. Here we take a root out of this equation and find here that x equals to the square root of 36, that is 6. PM is equal to x is equal to 6 units in its length. MQ is also equal to x is equal to 6 units in its length. In the next step, we will implement the Pythagoras theorem on this small right triangle BMQ. Again, we implement the Pythagoras theorem on this small right triangle BMQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the progression for Pythagoras theorem. So in this small right triangle BMQ, according to the Pythagoras theorem, BM squared, that is the square of the hypotenuse, is equal to BQ squared plus MQ squared. And again, in the right small triangle BMQ, according to the Pythagoras theorem, BM squared, this is the square of the hypotenuse, is equal to BQ squared plus MQ squared. BM is the missing side, so we leave it as it is, so it is BM squared is equal to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16, plus MQ squared. MQ is 6, therefore MQ squared is 6 squared, that is 36. So in total we should find out that BM squared equals to 16 plus 36. 16 plus 36 is 52. So BM squared equals to 52. Here we take out of this equation and finding out that BM, the missing hypotenuse BM, is equal to the square root of 52 units in its length. This is slide BM that equals to the square root of 52 units in its length. In the next step, we will implement the Pythagoras theorem on this right big triangle APM. Here by PT is the progression for Pythagoras theorem. So in the big right triangle APM, according to the Pythagoras theorem, AM squared, this is the square of the hypotenuse, is equal to AP squared plus PM squared. And again, in the big right triangle APM, according to the Pythagoras theorem, AM squared, that is the square of the hypotenuse, is equal to AP squared plus PM squared. AM is the missing side, so we leave it as it is. So it is AM squared is equal to AP squared. AP is 9, therefore AP squared is 9 squared, that is 81, plus PM squared. PM is 6, therefore PM squared is 6 squared, that is 36. So in total we shall find out that AM squared equals to 81 plus 36. 81 plus 36 is 117. So AM squared equals to 117. Here we take a root out of this equation and finding out that the missing hypotenuse AM is equal to the square root of 117 units and it's there. This is side A here, and is equal to the square root of 117 units and it's there. Our task is to find out the area of this ray shape. This ray shape is actually the right ray triangle A and B. So we have to find out the area of this green right triangle A and B. The area of the green right triangle A and B will be equal to the base MB times the height MA over 2. And again, the area of the green shape is actually the area of the green right triangle A and B, and the area of the green right triangle A and B equals to the base MB times the height MA over 2. We already found out that MB is equal to the square root of 52 units in its strength. Times the height AM. We already found out that the height AM is equal to the square root of 117 units in its length. Divided by 2. So in total, we should find out that the area of the green shape, this is actually the area of the right triangle A and B is equal to the square root of 52 times the square root of 117 over 2. We have the algebraic identity that says that the square root of A times the square root of B is equal to the square root of A times B. And again, the square root of A times the square root of B is equal to the square root of A times B. So according to this algebraic identity, we get that the square root of 52 times the square root of 117 is equal to the square root of 52 times 117 divided by 2. 52 times 117 is 6084 divided by 2. So in total, if you found out that the area of the green shape is equals to the square root of 6084 over 2. The square root of 6084 is equal to 78 divided by 2. 78 over 2 is 39. So in total, if you found out that the area of the green shape, that is the area that we are looking for in this question, the area of this green shape is equal to 39 square units in its size. So in the one, if you found out that the area of the green shape, that is the area that we are looking for in this question, is equal to 39 square units in its size. That's also the second question. In the next step, as I the lecture, I'll start with the first question, of course. task in the first question. Is to find out there are this big pentagon ABCDE. Okay, this is the big pentagon ABCDE. So what is a pentagon? A pentagon is a closed plate shape with two straight sides and two interangles. Again, a pentagon is a flat closed shape with 5 straight sides and 5 interangles. This is pentagon ABCDE. It says 1, 2, 3, 4, 5 sides and 5 interangles. 1, 2, 3, 4, 5. So in the drawing we have the big pentagon ABCDE. Note that those two angles are both right angles. ED equals to EA equals to BC. They are both equal to 1 unit in their lengths. DC equals to X. AB also AB equals to 1 minus X. Again, our task is to find out they have this big pentagon ABCDE. The first step, we join points E and B together by a straight line, and we also join points E and C together by a straight line. In the next step, we extended side BA of this pentagon ABCDE. We extended side BA by a straight line in such a way that the extended part AM will be equal to X unit in itself. Again, the extended part AM is equal to X units in itself according to our construction. BA, it is one side of the big quadrilateral ABCDE, and therefore it's the side of a quadrilateral. Again, BA is one side of the big pentagon ABCDE. So BA is a side of a pentagon. It is absolutely a straight line. When you extend the straight line by a straight line, the result BM must be also a straight line. So BM is a straight line. If you focus on the upper side of the straight line BM at point A, here the sum of the angles must be equal to 180 degrees according to all three. All three state that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BM at point A? We have this angle that is equal to 90 degrees in size, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we join points E and M together by a straight line. By joining points E and M, we created the right triangle EMA. In the next step, we prove that those two right triangles can go into each other according to side angle side rule. So why those two right triangles can go into each other? First of all, those two sides are both equal to 1 and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides are both equal to X and therefore they are equal to each other. So if you found out that those two sides and the angle that is included between those two sides in the right great triangle EAM are correspondingly equal to those two sides and the angle that is included between those two sides in the right great triangle EDC. And therefore those two right triangles can go into each other according to side angle side rule. We have those two sides and the angle that is included between those two sides in the right triangle EAM are correspondingly equal to those two sides and the angle that is included between those two sides in the right triangle EDC. And therefore those two right triangles can go into each other according to side angle side rule. So again, if you found out that triangle EMA, right triangle EMA can go into the right triangle EDC according to side angle side rule. From the fact that those two right triangles can go into each other, we derive two things. The first thing that we will derive that they have the same areas. any two triangles that can join to each other must have the same areas. That is to say, the area of this triangle, the area of this right triangle EAM is equal to the area of this right triangle EDC. And again, the area of the green right triangle EMA is equal to the area of the green right triangle EDC, because they have the same, they can join to each other, and therefore they must have also the same area. So the area of the green right triangle EMA is equal to the area of the green right triangle EDC. And the second part, the second thing that we got from the fact that those two right triangles can join to each other is that side EM is equal to side EC. EM equals to EC. EM equals to EC according to the rule that corresponding sides that can join triangles are equal to each other. Those two triangles can join to each other, and therefore those two corresponding sides, that is to say EM and EC, must be equal to each other and their lengths. Okay? So because of the fact that those two right green triangles have the same areas, it means that if we define the area of this green right triangle EAM as Z, that is to say it is equal to Z squared to the side, then the area of this green right triangle EDC must be also equal to Z squared to the side, because the area of those two green right triangles are equal to each other. Okay. So in the next step, we found out the length of side AB. AB in total equals to MA plus AB. And again, MB equals to AM plus AB. So MB in total equals to AM equals to X plus AB. AB equals to 1 minus X. So in total, MB equals to X plus 1 minus X. X minus X is also left only with 1. So 970 MB equals to 1 unit in its length. In the next step, we prove that those two triangles can join to each other according to side rule. That is to say, we prove that this right triangle EMB can join to this right triangle EBC according to side rule. So all those two triangles can join to each other. First of all, side MB of triangle EMB is equal to side BC of triangle EBC. They are both equal to 1, and therefore they are equal to each other. In addition, we just like now found out that those two sides are equal to each other. That is to say, EM is equal to EC. And finally, side EB is a common side that belongs to both triangles, so we can write down that EB equals to itself is a common side that belongs to both triangles. So if you found out that all the three sides of this triangle EMB correspond equal to all the three sides of this triangle EBC, and therefore those two triangles can join to each other according to side rule. Okay, again, if you found out that triangle EMB can join, this is the side can join to triangle EBC according to side rule. And from the fact that those two triangles can join to each other, we derive that they have also the same areas. That is to say, the area of this triangle EMB is equal to the area of this triangle EBC. And again, we derive that the area of triangle EMB is equal to the area of triangle EBC, because they can join to each other. In the next step, we calculated the area of this triangle EMB. The area of triangle EMB must be equal to the base of the triangle that is MB times the height AE over 2. So again, the area of triangle EMB must be equal to the base MB times the height AE over 2. MB is 1, AE is also 1. Again, MB is 1, AE is also 1, divided by 2. 1 times 1 is 1, so total the area of the triangle EMB is equal to 1 half. 1 half square root in size. But again, the area of triangle EMB is equal to 1 half square root in size. Here, wrote here that the area of triangle EMB is equal to 1 half square root in size. And from this equation, we derive that those two sides are equal to each other. That is to say, 1/2 is equal to the area of triangle ABC. So the area of triangle ABC is equal to 1/2 square units in size. So the areas of those both triangles, they are both equal to 1/2 square units in their sizes. This is triangle EMB is equal to 1/2 square units in size, and this is triangle EBC, this is also equal to 1/2 square units in size. In the next step, we focused on this big quadrilateral EMBC. What is the area of this big quadrilateral EMBC? Actually, the area of the big quadrilateral EMBC must be equal to the sum of the areas of the shapes that it consists of. And again, the area of this big quadrilateral EMBC must be equal to the sum of the areas of the shapes that it consists of. Actually, the big quadrilateral EMBC consists of two shapes, those two shapes. And therefore, the area of the big quadrilateral EMBC must be equal to the sum of the areas of those two shapes. This is to say it must be equal to the area of this triangle EMB plus the area of this triangle EBC. Okay, I read again. The area of the big quadrilateral EMBC must be equal to the sum of the areas of the shapes that it consists of. The big quadrilateral EMBC consists of two shapes. Only two shapes and not anything else. It consists of triangle EMB, and the second shape is triangle EBC. And therefore, the area of the big quadrilateral EMBC must be equal to the area of the first shape, that is the area of triangle EMB, plus the area of the second shape, that is the area of triangle EBC. We already found out that the area of triangle EMB is equal to 1/2 square units in size, plus the area of triangle EBC is also equal to 1/2. 1/2 plus 1/2 is 1. So in total, we found out that the area of the big quadrilateral EMBC is equal to 1 square unit in its size. Here, the area of the big quadrilateral EMBC is equal to 1 square unit in its size. That is from one side, but from the other side, we can look on this big quadrilateral in another way, and we find out that the big quadrilateral EMBC consists of two other shapes. It consists of this shape that is actually the green triangle EMA. It also consists of this shape that is quadrilateral ABCE. Therefore, the area of this big quadrilateral EMBC must be equal to the sum of the areas of those two shapes that it consists of. This is right, the area of the big quadrilateral EMBC must be equal to the area of this green triangle EMA plus the area of this quadrilateral ABCE. And again, if we look on quadrilateral EMBC in another way, we get that the area of the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. It consists of two shapes. The first shape is triangle EMA, and the second shape is quadrilateral ABCE. And therefore, the area of the big quadrilateral EMBC must be equal to the area of the first shape, that is the area of triangle EMA, plus the area of the second shape, that is the area of quadrilateral ABCE. And from this long equation, we know that those two sides are equal to each other. That is to say, 1 equals to the area of triangle EMA plus the area of quadrilateral ABCE. Repeat again, 1 equals to the area of the green triangle EMA plus the area of quadrilateral ABCE. But we only found out that the area of this quadrilateral, the area of this green triangle EMA is equal to Z, or it is equal to Z according to our definition. It is equal to Z squared in size according to our definition. So we can substitute the area of the green triangle EMA by Z, because it is equal to Z. And we get that 1 equals to Z plus the area of the big quadrilateral ABCE. Read again. In conclusion, we found out that 1 equals to Z plus the area of the big quadrilateral ABCE. but we already found out that z plus the quadrilateral ABCE okay, again, we found out that z plus the quadrilateral ABC equals to 1. Our task is to find out the area of this big pentagon ABCD. What is the area of the big pentagon ABCDE? The area of the big pentagon ABCDE must be equal to the sum of the areas of the shapes that it consists of. The big quadrilateral and the big pentagon ABCD consists only two shapes. It consists of only those two shapes. The first shape is the green right triangle EDC, and the second shape is this quadrilateral ABCE. And therefore, the area of the big pentagon ABCD must be equal to the area of this first shape, that is the area of the green right triangle EDC, plus the area of the second shape that is consists of, that is actually the area of quadrilateral ABCE. And again, the area of the big pentagon ABCD must be equal to the sum of the areas of the two shapes that it consists of. It consists of the right triangle EDC, and it also consists of quadrilateral ABCE. It consists of only those two shapes and not anything else. And therefore, the area of the big quadrilateral ABCD must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is the area of triangle EDC, plus the area of the second shape, that is the area of quadrilateral ABCE. According to what we already found out, is that the area of this green right triangle EDC equals to z squared in size. So I can substitute the area of the green right triangle EDC by z because it is equal to z. I get in total that the area of the big pentagon ABCD equals to z plus the area of quadrilateral ABCE. And again, the area of the big pentagon ABCD in total equals to z plus the area of quadrilateral ABCE. But we already found out that z plus the area of quadrilateral ABCE equals to 1. So z plus the area of quadrilateral ABC equals to 1 according to what we already found out. And from this long equation, this is one long equation, we derive that the area of pentagon ABCD equals to 1 squared in size. Okay, again, we found out that the area of the big pentagon ABCDE is equal to 1 squared in size. The area of this big pentagon ABCDE is equal to 1 squared in size. So we finish with the first question. The next step, I'll repeat on the second solution of the second question. Our task in the second question is to find out the area of this green shape. Actually, the green shape is the green triangle A and B. So we have to find out the area of this green triangle A and B. In the domain we have a circle. This is called AB. That is the diameter of the circle. AB is the diameter of the circle. In addition, we know that PQ is a tangent to the circle at point M. Point M is the point of tendency of tangent PQ with this circle. In addition, we know that those two angles are both right angles. We also know that AP equals to 9 units in its length, PQ equals to 4 units in its length. Again, our task is to find out the area of this green shape that is actually the green triangle A and B. So first of all, we implemented rule 7 in our drawing. According to rule 7, any peripheral angle that subtends of the diameter of the circle must be equal to 90 degrees in its side. This is peripheral angle A and B that subtend on the diameter of the circle. This is called AB, and therefore it is equal to 90 degrees in its side according to rule 7. The next step, we define this angle PA AM as alpha. So in the right triangle APM, the right peak triangle APM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in a triangle. So PQ is a tangent to the circle at point M. So PQ is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PQ at point M? We have this angle that is equal to 90 degrees minus alpha. This is the right angle, plus this missing angle BMQ, total must be equal to 180 degrees according to all three. Repeat again, we should follow that 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ must be equal to 180 degrees according to all three. 90 degrees plus 90 degrees, it is 180 degrees plus the missing angle BMQ plus minus alpha, in total must be equal to 180 degrees. We have 180 degrees on both sides of this equation, so 180 degrees will get cancelled, and we have only if the missing angle BMQ minus alpha equals to 0. Here we added alpha to this equation, and we found out that the missing angle BMQ is equal to alpha degrees in its size. This is the missing angle BMQ is equal to alpha degrees in its size. So in this small right triangle BMQ, this angle equals to alpha. This angle equals to 90 degrees, and therefore this purpose, this angle equals to alpha. This angle equals to 90 degrees, and therefore this purpose angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Those two right triangles are similar to each other according to angle similar to. That is to say, the right peak triangle APM is similar to this right small triangle BMQ according to angle similar to. That is to say, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if you found out that all the three angles of this big right triangle APM, of course, won't be equal to all the three angles of this small right triangle BMQ, and therefore those two right triangles are similar to each other according to angle similar to. So repeat again, if you found out that the right big triangle APM is similar, this is the sign of similar, to the right small triangle BMQ according to angle similar to rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. AP equals to 9 over MQ. MQ is the missing side of electricities, and it is equals to PM. PM is also the missing side of electricities over BQ. BQ is 4 according to what is given as the question. So in total, we have found out that 9 over MQ equals to PM over 4. Here we cross multiply this equation and found out that MQ times PM equals to 9 times 4, that is 36. Repeat again, MQ times PM equals to 36. In the next step, we defined the center of this circle. This point is point O, and OA is the radius of the circle that we defined as R. OB is also the radius of the circle, this is equal to R according to our definition. In the next step, we join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle, that is equal to R. the radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent PQ with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did a construction, that is to say from point O, that is the center of this angle, we draw perpendicular on side AP. Again, from point O, we draw perpendicular on AP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP. This point is point A. By doing this construction, we created the big quadrilateral LOMP. Inside the big quadrilateral LOMP, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, the total must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this 4 pieces again must be equal to 90 degrees in its size. So inside quadrilateral LOPM we have 4 rectangles, and according to rule 5, any quadrilateral that has 4 rectangles must be a rectangle, if not a square. So we relate to the big quadrilateral LOMP is a rectangle because it has 4 rectangles. In the next step, we did another construction, that is to say from point B, we draw perpendicular on the radius OM. Again, from point B, we draw perpendicular on the radius OM. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and the radius OM. This point is point S. By doing this construction, we created the small quadrilateral SBQM. Inside the small quadrilateral SBQM, we have 1, 2, 3 rectangles, and therefore this 4 pieces must be equal to 90 degrees in its size, and therefore the small quadrilateral SBQM is a rectangle because it has 4 rectangles. In the next step, we focus on the big rectangle LOMP. We know that the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMP, side LP is parallel to the opposite side OM. But LP is part of the straight line AP. Again, LP is part of the straight line AP and is parallel to OM. If a part of the straight line is parallel to another straight line, then the straight line AP itself must be parallel to the other straight line OM. So today we found out that AP is parallel to OM. Here, AP is parallel to OM. In the next step, I copied those two parallels AP and OM, and also the diameter AOB of the circle in the new page, and we implemented rule 50 in the new drawing. Those are the two parallels AP and OM. This is the diameter AOB. This is a copy from the original drawing. Those two angles are defined as corresponding angles, and they are located between the parallels AP and OM, and therefore they must be equal to each other in their sizes according to rule 50. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. So if you found out that angle PAO equals to beta, this is angle PAO, this is equal to beta, and we also found out that angle MOB also equals to beta. This is angle MOB, this is equal to beta. So in this right green triangle OSB, this angle equals to beta, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees times beta according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the upper right triangle ALO, this angle equals to beta, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees times beta according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two right angles can go into each other according to angle side angle rule. So why those two right angles can go into each other? First of all, those two angles are both equal to beta, and therefore they are equal to each other. In addition, side AO equals to side OB. They are both the radius of the circle, is equals to 1, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees times beta, and therefore they are equal to each other. So if you found out that those two angles and the side that is included between those two angles this right triangle ALO corresponding equal to those two angles and the side that is included between those two angles in this right triangle OSB. Therefore, those two right triangles can go into each other according to angle side angle rule. We have those two angles and the side that is included between those two angles in the right triangle ALO corresponding equal to those two angles and the side that is included between those two angles in the right triangle OSB. Therefore, those two right triangles can go into each other according to angle side angle rule. So if you again, I should hold on that triangle ALO and go into triangle OPS according to angle side angle rule. And from the fact that those two right triangles can go into each other, we know that LO equals to SB. LO equals to SB according to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles can go into each other, and therefore those two corresponding sides, that is to say LO and SB, must be also equal to each other in their lengths. That is to say LO equals to SB. And again, I should find out that LO equals to SB. So if you define the length of side LO as x, then the length of side SB must be also equal to x, because they are equal to each other. We also know that the opposite sides of the rectangle are equal to each other. So in the big rectangle LOMP, side LO must be equal to the opposite side PM, but LO equals to x, therefore the opposite side PM must be also equal to x units in its length. Likewise, in the small rectangle SBQM, side SB must be equal to the opposite side MQ, but SB equals to x, and therefore the opposite side MQ must be also equal to x units in its length. We already found out that MQ times PM equals to 36. MQ is x, MQ is x, PM is also x. And again, MQ is x, PM is x. So in total, MQ times PM equals to x times x, that is 36. X times x is x squared, so x squared equals to 36. Here we took out all of this equation and finally found out that x equals to the square root of 36, that is 6. So here x equals to 6 and here also x equals to 6. The next step implemented the Pythagoras theorem on this small right triangle BMQ. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle BMQ, BM squared, that is the square of the hypotenuse, must be equal to BQ squared plus MQ squared. Again, in the right triangle BMQ, according to the Pythagoras theorem, BM squared, that is the square of the hypotenuse, equals to BQ squared plus MQ squared. BM is the missing side, so limit is it is. So it is BM squared, that equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16. Plus MQ squared. MQ is 6, therefore MQ squared is 6 squared, that is 36. So in total, if you found out that BM squared equals to 16 plus 36, that is 52. So BM squared equals to 52. Here we took out of the equation, and finally found out that BM equals to the square root of 52 units in its length. This is side BM, that equals to the square root of 52 units in its length. In the next step, we refer to the Pythagoras theorem on this big right triangle APM. According to the Pythagoras theorem and the big right triangle APM, AM squared, that is the square of the hypotenuse, equals to AP squared plus PM squared. And again, the big right triangle APM, according to the Pythagoras theorem, AM squared, that is the square of the hypotenuse, equals to AP squared plus PM squared. AM is the missing side, so we notice it is. So it is AM squared equals to AP squared. AP is 9, therefore AP squared is 9 squared, that is 36. Plus PM squared. PM is 6, therefore PM squared is 6 squared, that is 36. So in total, we found out that AM squared equals to 81 plus 36. 81 plus 36 is 117. So in total, we found out that AM squared equals to 117. Here we took out all of this equation, and we found out that the missing hypotenuse AM is equal to the square root of 117 units in its length. This is the missing side AM, this is equal to the square root of 117 units in its length. Our task is to find out the area of this green shape. The green shape is actually the right green triangle A and B. So we have to find out the area of the green right triangle A and B. The area of the green right triangle A and B must be equal to the base BM times the height M over 2. And again, the green shape is actually the right green triangle A and B. the area of the green shape must be equal to the base MB times the height AM over 2. So the area of rectangle, it is the base times the height over 2. MB is equal to 52, AM is equal to 417. So again, MB is equal to 52 and MA is equal to 417 divided by 2. We have the algebraic identity that says that the square root of A times the square root of B is equal to the square root of A times B. According to this algebraic identity, we get that the square root of 52 times the square root of 117 is equal to the square root of 52 times 117 divided by 2. 52 times 117 is equal to 684. So in total, if you order the area of the green shape equals to the square root of 684 over 2. The square root of 684 is equal to 78 divided by 2. 78 over 2 is 39. So in total, if you order the area of the green shape, it is equal to 39 square units in size. Okay, then the area of the green shape it is equal to 39 square units in size. The area of this green shape, that is the area that we are looking for this question, is equal to 39 square units in size. Okay, thank you very much.